Now we'll see some problems related to this, mapping techniques to understand them clearly. Okay. So first we see this problem. How many total bits are required for a direct mapped cache? So this is important. It's a direct mapped cache with 16 KB of data and 4 word blocks, assuming a 32-bit address. Okay. So address size is 32-bit and cache size is 16 KB. Whenever they say that cache size is 16 KB, especially they clearly mention that it is 16 KB of data. So that means, so the other bits we should not consider. That means tag bits we should not consider in this 16 KB and that valid bit we should not consider. Okay. Now we will see the more details about this problem. First thing, the question is about how many total bits are required. Data bits are given 16 KB, but how many total bits are required for a cache is the question. So in a cache, what are the things we will be having if the mapping technique is direct? So for every block, you will be having a tag, right? That means number of tag bits are required to find out the size of the cache. Apart from that, I told you that there will be a valid bit. I am assuming that, let's say, so valid bit also to be counted. Sometimes, in the question they will clearly mention what are the bits present in the cache. Okay. Now I am assuming for this problem, okay, this is not a gate problem, that's why it is not completely clear, but in the gate exam they will mention what is the structure of the cache. That means what are the fields we have in cache. Okay. So I am assuming in this problem valid bit, tag and data. Okay. So this is the assumption. For this, assumption we are solving the problem. Okay. Now don't question this assumption. Don't ask me, so why valid bit? Okay. So in the question it is not given, right? But I am assuming that, let's say, valid bit is there and I am solving it. But in the gate exam they will clearly mention whether to take valid bit or not, whether tags to be taken or not, everything. Okay. Now for this problem I am solving. The question is how many total bits are required for a complete cache. Now assume that, let's say, you have one block. There are a lot of blocks, but for this particular block, then how many bits are required? How many bits you are storing in this block? Valid bit, 1 bit, right? Number of tag bits. That means we have to calculate number of tag bits. And what is the size of the data in this block? Did they give anything? No. The total cache size is given 16 KB, right? And each cache block size 4 words. We should remember. Okay. Now, sir, our system is byte addressable, otherwise word addressable. Which one we have to take, sir, in the question? If nothing is mentioned, go for word addressable system. Okay. Otherwise, they will mention that system is byte addressable. In the problem, nothing is mentioned, right? Then I am going to solve this problem with two cases. One is byte addressable system, second one word addressable. Let us begin with word addressable system, which is easy to answer. First, word addressable system. In word addressable system, what happens? Every word gets one memory address. Remember it. Okay. Now, here interesting thing is we have to find out the divisor, like how many bits are required for word offset. If it is really word addressable system, then your main memory address is divided into 3 parts. Okay. I'll show that. So your main memory address we are going to divide logically into 3 parts. One is for these bits for word offset, okay, to identify which word. Now, remaining memory address will be divided into 2 parts. We know that because it's a direct map technique, then we have to divide that into 2 parts. One is cache offset, otherwise cache index bits, then tag bits. So how to find out each and everything we will see. From now onwards, whenever you have a direct mapped problem, divide the main memory address into 3 parts. Okay. So the first part is word offset. The remaining part is nothing but block number, main memory block number. That is further divided into 2 parts, tag and cache index. Okay. This cache index depends on the number of cache blocks. Okay. Word offset depends on the number of words in the block. Now we begin with this one. 4 word blocks. That means each cache block has 4 words. Word 1, word 2, word 3, word 4. Since our system is word addressable system, then how many bits are required to differentiate them? 2 bits are required, right? In the main memory address, 2 bits we can dedicate for word offset. Based on that, appropriate word can be selected. So 0001, 1011. You understand that point, right? So finally we got word offset as 2 bits. Right. Now cache index, this cache index depends on the number of cache blocks. That's why we have to compute number of cache blocks. So what is the information we have? We have total cache size 16 KB, right? So this 16 KB is specially only the data part. So we will be then in each block how many words we are writing? 4 words. Okay, remember it, 4 words. So in this problem, generally if nothing is mentioned, word size we have to take 4 bytes, remember it. Okay, so because majority of the modern architectures have word sizes 4 bytes. So 4 words means what? Each word is 4 bytes, then 4 words means 16 bytes. Now try to understand. So cache size is 16 KB, especially words, right? That means only data. So in 16 KB, how many words we have? In each block? 4 words. That means each block is consuming 16 bytes. Let me divide that with 16 bytes. What you get? The total number of bytes are 16 KB in the entire cache, but each block contains 16 bytes. Then if you divide 16 KB by 16B, you get number of cache blocks. Understand? Example, the total number of bytes in your cache is 32 bytes, but each block contains, let's say, 4 words. 4 words means 16 bytes, but total 32 bytes we have. Then how many blocks will be there? For that we have to divide by 32 bytes by 16 bytes. In the same way, whenever you want to find out from now onwards number of cache blocks for a problem, first find out the size of the cache. Okay, 16 KB. It's specially size of the data in the cache. Size of the data in the cache by total number of size of the data in the block. If you divide, then you get number of blocks. BB will be cancelled, then 16 will be cancelled. You got K. K means 1024, right? So number of blocks finally 1024. We should remember it. So when you have 1024 blocks like this, then how to index the right block? To index the right block, then 10 bits are required, and we know that this 10 bits we are going to use, and we have seen examples for that, right? Always we take these 10 bits to decide which block our main memory address will go, right? So cache index finally size will be 10 bits, right? So the third thing is tag. Tag size is nothing but total number of bits in your main memory address, which is nothing but 32, which is given out of 32. Remove this cache index 10 bits and word offset 2 bits. 32 minus 10, 22. 22 minus 2, 20. So tag bits are 20. In the word addressable system, number of tag bits are 20. Now we got this 20 bits, 1 bit here. And what is the size of the data in bits? I would like to find out everything in bits. Data size already we know 16 KB overall, but each cache block size 4 words. 4 words means 16 bytes, correct? So 16 bytes. If I divide it into bits, it will be 16 into byte means 8 bits. It would be 128 bits. Now finally I got a block size 128 bits here, pure data, and tag 20 bits, 1 for valid bit, right? So finally 128 plus 20, 148, 148 plus 1, 149. So 149 bits are required in a block. The question is how many total bits are required? This I can say overhead. This is original data. This is extra information we require to correctly get the data, right? Now I can say one thing. Simple. The total number of bits in your overall cache equal to how many blocks we have. How many blocks we have? Just now we have calculated, we have 1024 blocks, right? Into, in each block we have 1 valid bit, 20 tag bits and 128 data bits. Then if you simplify it, you get 1024 into 120, 149. Now let me solve this problem in a one more way. That means by assuming that it is byte addressable system. If it is word addressable system, this is the answer. Now let us assume this is byte addressable system. If it is byte addressable system, what are the modifications we are going to get? We will see. In byte addressable system, every byte gets, this is important because sometimes in the question they will mention that it is byte addressable system. In byte addressable system, what happens? Only the thing is addressing will be different. Every byte will have one memory address, you remember. Okay, if this is your 32-bit memory address, okay, then every byte is going to get a number, then I can say one thing. What is the size of your block, cache block? So here cache block size is 4 words, right? Let us repeat, 4 words. 4 words means 16. Each word is 4 bytes, then 16 bytes, correct? I can say like this. So finally you have 16 bytes in your cache block, right? Now, so to address that 16 bytes, because every byte is going to have separate number, then to differentiate that 16 bytes we need how many bits? 4 bits. Okay, the same thing I can represent like this. Because it is a byte addressable system, then you will be having two further classifications. One is first word offset, which word you want, because each cache block has how many words? 4, right? So how many bits are required to decide which word it is? 2 bits. Now I want 2 more bits. Why, sir? Once I identify the word, right, I should find out the correct byte also, correct? Because it's a byte addressable system, then sometimes I should be able to find out the right byte, because any byte I can access. Then if I want to access a particular byte, then how many bits are required? Because there are 4 bytes, right? Then 2 more bits are required. So finally, if the problem is about byte addressable system, in the byte addressable system, then we have to consider bits for byte offset. This is called byte offset. Otherwise, blindly remember one thing. If the problem is about byte addressable system, what you have to do, we have to take some bits for byte offset, some bits for word offset. First I will tell you how many bits we have to take for byte offset. This would be good. Okay, don't worry too much, because if you, what is byte offset is nothing but in a word how many bits are required to differentiate your byte. In a word how many bytes we have? 4 bytes, correct? Byte 1, byte 2, byte 3, byte 4. In byte addressable system, the only thing is every byte is getting a number, right? Every byte should be differentiated. That's why we are addressing everything. That's why how many bits are required to separate these 4 bytes, to differentiate these 4 bytes? 2 bits. Using these last 2 bits we will decide whether our byte is this one or this one. In that way we can differentiate a particular byte. Fine. Now in the remaining part of the main memory address we want 2 more bits. Why, sir? Because I want to find out a particular word in a block. In a block how many words we have? 4. To identify the right, once you come to the block, to identify the right word, then you require 2 bits. I can say 0 0 this one, 0 1 this one, 1 0 this one, 1 1. In that way, using 2 more bits I can differentiate the word. Now see, let me summarize. Using 2 bits I will come to the particular word. Using other 2 bits I will come to the particular byte. So that is what the meaning of byte addressable system. So that's why 2 bits here, 2 bits here, 4 bits are required. Then how many total bits we have? 32. Out of 32 bits, 4 bits are gone. Then remaining bits are 28. Out of 28, so some bits for cache index, because it is direct mapping. So cache index field and tag field, remember it. How to decide cache index field? It depends on the number of cache blocks you have. So we have not changed number of cache blocks. So that's why 10 bits. Already we have seen that we have 1024 cache blocks. Now comes tag field. So tag is easy. 10 plus 2 plus 2, 14 bits are gone. Then remaining bits for tag. Then the solution will be 18 bits for tag. Using that we solve this problem. So same formula, 1024 blocks. Each block has this structure, 1 bit for valid bit and this time 18 bits for tag, right? Plus data. We have data of size, already we have seen, right? 16 into 8, 128 here, okay? If you have a doubt, just check it out. It is 4 word block size, 4 words. We have 4 words here, 1 2 3 4. 4 into 4, 16 bytes, correct? So 4 into 4, 16 bytes. Finally we converted this data into bytes. To convert it into bits, that is what we are doing, because we have valid bit and tag bits, everything in bits. That's why I'm dividing it into bits. 16 bytes are, if they are divided into bits, that will become 128 bits, right? So 128, 146, 147. So answer is 1024 into 147. Otherwise 147 kilobits. Okay. From now onwards you remember these two techniques. If the problem is about byte addressable, we should do like this. If the problem is about word addressable system, we have to do like this. That's the difference. Okay. There is a small difference. Understand? So this is about direct mapping problem. Understand? We'll see some more direct mapping technique problems to understand the things clearly. See this question which is asked in GATE 2011 paper. An 8 KB direct mapped cache which is write back cache. See, this information is unnecessary. Okay, don't worry about it. I am going to teach you write back cache after these problems. Okay. So we have given 8 KB direct mapped cache. Ignore write back. Is organized as multiple blocks, right? So these are all, let's say, various blocks, and each size of 32 bytes. Whenever they say that cache block size 32 bytes, we should think that it is about data. Okay, so the data is 32 bytes. The processor generates 32-bit address. We have 32-bit address. Fine. Next, the the total cache size is 8 KB. Remember, again this 8 KB comprises only data. Okay, so we have some tag information that is not counted here. Now the cache controller contains the tag information. What is tag information? For each cache block comprising the following. Okay, one is valid bit, one valid bit, one modified bit. So anything else? As many bits as the minimum needed to identify memory block in the cache. We know that to identify the memory block in the cache, the minimum bits required, that means one more meta information which is required is tag, correct? So finally, he clearly said that each cache block is going to have tag bits, right, and valid bit, modified bit. That is what he mentioned. So valid bit and modified bit he has clearly mentioned, but he added as many bits as the minimum needed to identify memory block. We know that to identify the right memory block we need tag bits, correct? Because multiple candidates are going to present in this cache block. We don't know who is currently residing. To differentiate them, we use tag bits, correct? So finally, we have to find out the number of tag bits also. For that, we have to divide it into 3 parts. We know the remaining story. There are 2 cases I told you. One is we can divide this memory address into 3 parts or 4 parts. In the 3-part model, we are assuming that the system is word addressable. Okay. So solve this problem by assuming word addressable, and solve this problem by assuming byte addressable, because nothing is mentioned, right? Let us assume first of all the system is word addressable. That means every word gets number. Okay. With that we try to solve. If every word gets number, then how many words we have in a cache block? Did they mention? Yes, 32 bytes. Since cache size is 32 bytes, then to number them, and what is the word size? We know that always word size will be 4 bytes. We can assume like that, not a problem if they don't mention. So since word size is 4 bytes and cache block size 32 bytes, then how many cache entries will be there? 8 cache entries, correct? That means 8 words. To differentiate 8 words within the cache block, how many bits are required? 3 bits. That is nothing but word offset. Okay. Now we got word offset. Now second thing, cache index. Cache index depends on the number of cache blocks. We have to identify now number of cache blocks. The story is very simple for number of cache blocks. What is original cache size? 8 KB. Then each cache has dash of size 32 bytes, right? 32B. Then if you divide the cache block size by total cache size, you get number of cache blocks. You remember this formula, okay? So 8K by 32, 8 4s are 32. Then 1K means 1024 by 4, which is nothing but 256. So 256 blocks are available. To differentiate them, we require 8 bits. Finally, we got word offset, cache offset. The third thing, tag, correct? Remaining bits are tag. So we have 32 bits, 8 plus 3, 11 gone, the remaining bits are 21 bits. So these 21 bits are going to be tagged. Now the question is about metadata, right? So what is metadata? Tags. Tags are valid bit, modified bit, the tag offset, correct? So finally, each cache block is going to have one valid bit, one modified bit, and we know that one tag, right? So how many bits are required in tag field? 21. 21 plus 1, 22. 22 plus 1, 23. So finally 23 bits of meta information for each cache block. How many such cache blocks we have? We know that already, 256. So answer would be 23 into 256. See, 3, 6, 8 in the last digit supposed to be 8 in the options, but nothing is matching. That means this method is wrong. Why? Because we know that there are two possibilities. Maybe his examiner is thinking that it is word addressable system. Second one, examiner might be thinking byte addressable. Since word addressable model is not working, then we go for byte addressable system. So let us go for byte addressable system. In byte addressable system, what happens is, now we have bytes. So we will be having byte offset, correct? In the word. So we can do like this. Either we can divide it into 4 parts or 3 parts, anything. So you can even divide it into 3 parts. When you divide it into 3 parts, then this is going to be byte offset. Okay. Now we have to worry about bytes, byte addressable system, right? Byte offset within a word. Otherwise within a cache block. Anything is fine. Okay. Now you can use this for byte offset in a cache, otherwise byte offset in a word. Okay, let me go with the usual model. Okay, let me divide like this. First we have byte offset. Okay, so we in a word, how many bytes will be there? 4, correct? Then how many bits are required for byte offset? 2 bits, remember. Okay, so these 2 bits I use whenever once I get a word. Okay, but how to get a word? We should go to the cache. In cache, how many words are there? Think about it. So we have how many words in the cache? Recall, we have 32 bytes. Out of them, how many words they will form? Divide by 4 bytes. Then you get number of words. Bytes will be cancelled. Then 8. That means what? There are 8 words. To differentiate 8 words, otherwise to properly index one of the 8 words, we require 3 bits, right? So that's why in that way. So finally 3 bits for word offset. Byte offset 2 bits. 3 plus 2, 5. Either you can separate like this, otherwise directly you have 32 bytes. To really find out the right byte at any time, so we have 32 different bytes, then 5 bits are required. So either go that way, either follow this method. Okay. Now, so finally, once you have a word, we can find out the byte also. Now we know the remaining bits. What are they? Cache index. Second one, tag. So cache index directly depends on number of cache blocks, 256. That means 8 bits. So 8 plus 3, 11, 11 plus 2, 13. 13 are gone. Then remaining bits are 19 bits. So finally, tag contains 19 bits. Now you see. So in this 19 bits, these 19 bits are only for one cache block, correct? Remember it. Now let us focus on one particular cache block. In what particular cache block? Metadata is 19 tag bits, 1 valid bit, 1 modified bit, to 21 into how many such cache blocks we have? 256. So if I simplify it, you get 21 into 256. So if I simplify it, you get 5376. You just try it out. So that's why option D is the right choice. Understand? Now remember one thing. Right, whenever this kind of question is given, we have two models. We can assume word offset and solve it. Second one, we can assume byte offset, byte addressable system and solve it, correct? So because nothing, we don't know the mind of the examiner at this moment, or at that moment what examiner is thinking, no one knows. Then what to do? Try in both ways. So one of them should match. Understand? And one more thing, sir, I tried byte addressable model, second one word addressable model. We have, let's say there are two options. One is matching for byte addressable way. Second one is matching for word addressable model. Then which one is correct? So we can't decide anything. Understand? Most of the times they don't give that like that. Okay, right? This is about this problem. Now we'll see some more problems. We'll see one more question. So this question is asked in GATE 2016 paper. Let us try this. The width of the physical address on a machine is 40 bits. The width of the tag field in a we have to find out this one. The width of the tag field in a 512 KB and 8-way set associative cache is dash bits. So finally we have to find out the number of tag bits. To answer this question, before that, sir, should we use word addressable model, otherwise byte addressable? So here directly go for byte addressable. From now onwards, you remember one thing. If nothing is mentioned, directly go for byte addressable model. Okay, so we can assume byte addressable. And If the question is about multiple choice, then solve the problem with byte addressable. If you get the answer, then just take it and go. If you don't get answer with byte addressable, then only go for word addressable. Okay, you follow this technique from now onwards. Okay, so finally, if nothing is mentioned, we can take it as byte addressable system. Okay, let us begin the problem. The width of the physical address on a machine is 40 bits. We have a 40-bit width physical address. Understand? Now we have to divide it into three parts, right? One is tag bits. Second one, set offset. We know that because it is set associative mapping. Third thing is this part is word offset, correct? So here word offset means finally byte offset. Byte offset. So we can use, we can say word offset also, no problem. Okay. So there is nothing in the name. So finally the meaning is, I will tell you. The word offset means here finally all these bits should be able to differentiate each byte separately. That's it. Okay. Now you have a cache block. Okay. Already I selected somehow using set offset, using tag bits. I have finally found one block. Okay. Don't worry too much here. You got already cache block. In that there is a byte because our systems are byte addressable, right? Now we have to find out a right byte. Okay. So you should be able to find out the right byte. For that, how many bits are required? So I will tell you one thing. Example, let's say you have only one byte here in the cache block size. So directly we can use this formula. You have only one byte, then one bit is enough. If you have 2 bytes, then that means byte 1, byte 2, then 1 bit is enough to differentiate 2 bytes. If you have 4 bytes, that means 1 word. Okay. If you have 1 word, then how many bits are required in the byte offset or word offset portion? Together, simple. So 1 word means what? How many bytes? 4 bytes, right? 4 bytes to differentiate 4 different bytes. How many bits are required? 2 bits. In that way we can find out the number of bits here. Understand? Now, example, one more final thing. Let's say you have 32 bytes in the block. 32 bytes. Then how many bits we will be fixing in the byte offset? Simple. 32. 5 bits. That's simple. Otherwise, you can use words and also you can understand. 32 bytes means we have how many words? 4 words. I mean 8 words, right? 8 words. Okay. So to identify the right word, we require 3 bits. After identifying the right word, still you want to further. Sometimes we require, sometimes we can stop here, but sometimes you want to go to a particular byte. That is the advantage of byte addressable system. In byte addressable system, sometimes you want to address a particular byte. Then how many more bits are required? 2 more bits. That's why finally, so 3 plus 2 with 5 bits, we can go to the right byte. Okay. Now, from now onwards, we use this shortcut. Find out the cache block size in bytes. If it's 32, then number of bits required in this word offset is 5 bits. Understand? Now, let us use this concept and we try to solve this problem. Finally, this word offset contains, let's say, W bits. Understand? Or byte offset, whatever. Set offset requires S bits. They did not give in the question. Assume that, let's say, tag bits are T bits. But we have T plus S plus W as dash 40 bits. That you remember. Second thing, equation 1. But we want this T value. How to find out T value where S is unknown, W is unknown? We have one more information, that is cache size. Cache size is 512 KB. So 512 KB is the cache size, but we can recalculate cache size with these parameters, set, offset and everything. You tell me what is the cache structure. We have in a cache some sets, correct? Because it is set associative mapping, we have some sets, right? In a set, how many blocks we have? It is a 8-way set associative mapping. In a 8-way set associative mapping, you will be having 8 blocks in a set. So now you tell me. So how many such kind of sets we have? We don't know, right? But you are fixing S bits here. If you are fixing S bits here, then how many different number of sets we can form? 2 power S. That means how many maximum sets we can address? 2 to the power of S, you remember. So finally, 2 to the power of S sets you might have in your cache. That's why you are using S bits. correct? Then each set is going to have 8 blocks. So total number of cache blocks in your cache is 2 power s into 8, correct? Let me revise. You have some sets. How many sets you might have? Because you are using s bits for s set of set, then 2 power s sets. So out of each set you have 8 blocks. That's why total number of blocks are 2 power s into 8, and each block has capacity of some bytes. We know one thing. So this w bits comes from where? For 32 byte cache system, 5 bits. 64 byte cache system, 6 bits, right? So similarly, for w bit cache system, here if you have the w bits, then 2 to the power of w bytes, correct? So I can say like this now finally. Each cache block has 2 power w bytes, and how many such cache blocks we have in one set? 8, right? 8 into 2 power w bytes are number of bytes in a set. How many such sets we have? 2 power s. So finally 2 power s into 8 into 2 power w bytes equal to 512 kb. Now here we have byte, here we have byte, gets cancelled. Then we have 512k. Let us simplify it. 864 is a 512. Then you get 2 power s into 2 power w equal to 64. Then s plus w will become, sorry, it is not 64. So it is 64k, right? Then if you simplify it, it would become 2 power s plus w equal to 64 is 2 power 6 into 2 power 10. So it would become 2 power 16. So here left hand side is s plus w. Then s plus w equal to 16. Remember this. But we have t plus s plus w is 40. Then s t value equal to 40 minus this 16. So 24 bits. So that's why 24 is the right answer. In that way, we can answer this question easily. Remember one thing, from now onwards, nothing is mentioned in the question about word addressable or byte addressable. Byte addressable is the default thing. See this problem which is asked in GATE 2014 paper. A 4-way set associative cache memory unit with capacity of 16 kb is built using a block size of 8 words. Okay. So in the problem, word size is not mentioned, but always you remember, word size you can take as 4 bytes. Okay. Now it is a 4-way set associative cache memory. Remember it. The word length is 32 bits. Of course, in the problem it is mentioned, but if it is not mentioned, then always we can take it as 4 bytes. The size of the physical address space is 4 GB. Understand? So here again I am assuming byte addressable system. That is default. In a byte addressable system, every byte will be numbered, correct? So here 4 gigabyte is the address space. 4 gigabytes I can say. You have finally 4G bytes. For every byte we need one number. Then for 4G bytes we require 4G numbers, right? So 4Z means 2 square into 2 power G means 30. So 2 power 32 bytes, right? So to number 2 power 32 bytes we require 32 bits. Quite obvious, right? So finally 32 bits is the address space. So in that address space, the question about the number of tag fields, right? So what we have to do is we have to divide it into 3 bits. We know that 3 parts. This is for tag. Since it is set associative, then it is set offset, right? Now the third thing is byte offset or word field. Okay. So in this word field, we require number of bits equivalent to number of bytes in the cache block. If you want to fill this word offset, directly go to cache block size. What is the cache block size? Did they give anything? 8 words, right? So 8 words, each word size 4 bytes. Then finally 32 bytes. Since we have 32 bytes, to differentiate each byte, then how many bits are required? 5 bits, right? So that is the concept of byte addressable model. So 5 bits here. Now we should find out set offset. So what is set offset? It depends on the number of sets in the cache. So how many sets we have? For that, first of all, we should find out number of blocks, correct? How many blocks we have? The size of the cache itself is 16 kilobytes, and you divide it by block size, which is 8 words. A word means 32, 4 bytes. So that's why 8 words means 32 bytes. So if you simplify it, you get 16 to the 32 kilo by 2, which is nothing but 512, right? K means 1024. 1024 by 2, 512. So we have 512 blocks. But I should know the number of sets, right? The number of sets, if you want to know, then you divide by the 4-way, right? The 4, right? So 512 by 4 is nothing but 128. correct? So 4-way means every 4 blocks as one set, correct? Then the number of sets equal to 512 by number of blocks in a set. So it would be 128. So to differentiate 128 sets, we require how many bits? So that's by 7 bits. So we are going to use 7 bits to index into the cache block. Sorry, set particular set. Now the tag bits 32 minus 12, 20. So finally 20 is the answer. See this question, which is asked in GATE 2006 paper. We have two cache organizations. First one is 32 KB set associative, and they have clearly mentioned that it is two-way set associative mapping with 32 byte block size. Remember one thing, the organization number one is set associative, especially two-way, and the block size is 32 byte. Okay, so in 32 byte, and one more thing, the complete cache size is given. The cache size is 32 KB. Okay, so 32 KB cache size. This is the data about set organization 1. The second is of same size but direct mapped. Everything same here also, organization 2, but it is direct mapped. So in that we have, I can say direct mapping is also a set associative mapping. How, sir? It's a one way, right? That means every set has only one block, right? So now second thing, the cache size, everything is same, and block size 32 bytes here also, and the cache size is 32 KB. Fine. Apart from that, anything is mentioned? They have given that there is a 2x1 multiplexer. If you use it, so what is the delay of the 2x1 multiplexer? It is 0.6 nanosecond. If we want, then we can use it. While a k-bit comparator, whenever you are comparing k-bit tag fields, okay, so example, we use comparators for comparing the tags, right? This is your comparator, k-bit. What is the delay for that? It is going to take two k-bit numbers and it is going to give the output after k by 10 nanoseconds. K by 10 nanosecond. Now the question is, the hit latency of the set associative organization is H1. So what is hit latency? I will tell you. Hit means what? Data is available. Data is available in the cache and you are searching for it. Okay. Then it takes some time to get it, right? Tell me what is the bottleneck involved in this finding the data in cache. If it is set associative, recall, because it is two-way set associative, I can show with simple picture. We have to first of all come to the right set, correct? Okay. So because no details are given how to come to, assume that, let's say that takes 0 delay. Very quickly, using very fast indexing, so we, let's say, came to the right set. Okay, in the right set we have two blocks. Which one is correct? To decide that, this tag field, let's say this block will have a tag field, this block will have tag field, these tags will be compared against our tag, correct? So there will be a comparator, one thing. Here also another comparator that will be connected like this, and in the your main memory address there will be a tag field, right? That will be connected here, and the same thing will be connected here, so that both comparators will work and they will decide whether data is available or not. Once you realize data is available, correct, these comparators will do that, then we will be selecting the right block, correct? So that right block we have to identify. For that we have to use multiplexer, correct? So multiplexer's input is what? How to select the right one? So based on what? This comparator results. Without comparator results, can we find out the right block? No, right? So first of all, comparators will give the result that whether data is available or not. Then later we will be using multiplexer, correct? Please recall, already I told you, I have given one circuit, okay, related to set associative mapping. Go through that, then you will realize the answer. Okay, so that circuit was like this. So we have used tag fields, correct? This is your block, this is another block, this block also will have tag field, this is your original tag. Okay, so let's say this is your original tag, this tag and this tag will be compared, this tag and this tag will be compared again here. Now based on the result, right, this one. So we use multiplexer. Using the multiplexer, so we will be selecting one of them, correct? So this multiplexer, I can say, is connected to this data and this data, and control lines are these comparator results. That's why we have to wait for the result of the comparators. So based on the comparator results, then we will select the right data. So for that we use multiplexer, which is 2 by 1 multiplexer, which is going to decide the right block. Out of two blocks, one will be selected. That's why 2 by 1 multiplexer, because in set associative mapping always the competition between two blocks, right? So this is the story. Now what is the delay? The delay, if you see comparator delay k by 10, which is given, I'm assuming that the comparator size is k. We have not calculated yet, right? So that takes k by 10 nanosecond plus one multiplexer delay 0.6 nanosecond, which is the answer for our H1. So k depends on the main memory size and everything, correct? Let us take main memory address size. What is given? 32 bits. Let us split it into three parts, correct? So this is word offset, correct? So this is set offset, this is tag. Let us find out everything. First of all, what is the size of the cache block? Cache block size is 32 byte, correct? I am assuming that word size 4 bytes, then there are 8 words, correct? So I can say that. Otherwise that is not required really. We have a shortcut. Since the cache size is cache block size 32 bytes, then since we are assuming always byte addressable systems, then 5 bits are required to finally to differentiate each byte, correct? So 5 bits per word. Now sets offset. Set offset depends on number of sets. How many sets we have? To understand that, we should find out the number of cache blocks. Cache blocks equal to size of the cache by block size 32 bytes. So byte gets cancelled, 32 cancel, 1k. So 1024 blocks, but each set contains 2 blocks. The number of sets are 1024 by 2, which is 512, right? So 512 sets can be identified by or indexed by 9 bits. 9 plus 5 14, then remaining tag bits are 18 bits. So finally k, which is nothing but size of the, what is k? You see, k bit comparator. So here we use k bit comparator, where k is nothing but number of tag bits. So number of tag bits are here 18. So 18 by 10 is nothing but 1.8. So 1.8 nanosecond delay for comparison, followed by 0.6 nanosecond for selection of data. So it would be 2.4 nanosecond. So option A is the right choice. If you know the circuit clearly, very easily we can solve CO questions. CO questions are lengthy, conceptual. If you remember the things, if you by heart the things, you can't answer any question. But if you know the inner details of any problem or any circuit, then you can easily answer the questions. So that's why from now onwards, you remember, whenever you are studying some theory, then you should understand from the basics. We should understand all the related. Example, if it is CO, then especially you should know the circuit related to every problem, I mean every organization, I can say. Okay, so that's why, since that I can say, since floating point numbers, I was giving all the circuits parts, right? So that if you have a clarity about the circuit, then very easily we can answer the questions.